Decohere, Daine Danielson, and Dan has been doing some cool stuff, as you will show in the next 40 minutes, with really smart people, as you can see in his first slide. So, Dan, please, you can start whenever you want. Right? Thanks.
Great, thanks. Can you guys hear me? I can tell you can hear me. Okay, so this is, well, I'm Daine. I'm a graduate student at the University of Chicago. And this talk is kind of a continuation of the talk that you heard from Gautam, which sets up a lot of the ideas that you'll see here. And the punchline of this talk is going to be that black holes and cosmological horizons decohere quantum, Superstitions is what I accidentally wrote into the email submission with my title. But I don't think most quantum superstitions that I've come across are fairly incoherent without the help of any horizons. So I'll be focusing on quantum superpositions in this talk. So I'm just going to start by reviewing something that should be very familiar. I'll review it very quickly from Gautam's talk, which is this thought experiment that motivates this whole thing. So in the distant past, Alice used a Stern-Gerlach apparatus to produce a spatial superposition of some massive or charged body with spin. And she's coming in here on the space-time diagram from below. And later she attempts an interference experiment and looks for signs of decoherence, kind of cartoon symbolized by this interference pattern here. And more concretely, she could do that by, for instance, looking for, she could measure spin along the x-axis, and since this is a definite up in the along the x-axis spin state, if she even once were to measure spin down along the x-axis, she would know that she had decohered to some degree. So that's how she's going to check for coherence. Meanwhile, in a space-like separated region from Alice's recombination process, there's going to be some other experimenter, Bob. And Bob is going to be trying to measure the superposed Newtonian or Coulomb field of Alice's superposed particle. Bob, is sitting in this stationary or static superposed Newtonian field, and he could, for instance, release a particle from a trap and become entangled with Alice's superposition to some degree. Okay. Now, this forces a sort of paradox, as we saw, which is that Bob can choose to measure to release his particle or not to release his particle. If Bob releases his particle and gets which path information, then by complementarity, Alice's particle has got to be decohered. But as we've just seen, Alice in this protocol can tell whether she's decohered. So this seems paradoxical, since Bob is at space-like separations from the recombination process. Okay, so as you heard, the resolution is that vacuum fluctuations and quantized radiation play a crucial role in resolving these kind of paradoxes of causality in quantum field theory and in linearized quantum gravity. That the vacuum fluctuations delocalize Bob's particle by some amount, and that means he needs to wait a sufficiently long time to distinguish which path his particle's on. And Alice, meanwhile, has to recombine the branches of her wave function sufficiently slowly that she doesn't decohere herself by radiation. And these two things balance to make sure that causality is always preserved. If Alice goes slower to minimize her radiation and then remain more coherent, then Bob has to measure from further away or over a shorter time in order to remain space-like from Alice. And both of those reduce his ability to tell which path he's on in the light of the vacuum fluctuations. So this resolves the paradox in flat spacetime. So we thought we had kind of wrapped up this whole story until we started thinking about what would happen if you tried to repeat these types of arguments in more exotic situations, like outside of a black hole. And there the story really changes. Because, well, if you put Bob behind a black hole horizon, eventually Bob will die, but I'm going to make it a big black hole so that Bob has enough time. Give as much time as he wants by making the black hole bigger and bigger. And so he has no problem integrating up enough time to overcome any local vacuum fluctuations of the field. And he's still going to be space-like. And meanwhile, Alice could take as long as she wants to recombine her superposition. That's not going to make any difference in the causal relationship between her and Bob. So she can recombine totally adiabatically and avoid emitting any radiation to scry. And now we've got, seemingly, the paradox back in our face. And it occurred to us that one logical way out, one loophole in the argument would be there'd be no paradox if Alice's superposition were to decohere at a constant rate as if she were becoming entangled with any number of optimally sensitive experiments that might or might not be hiding behind the event horizon. And that initially was just a loophole that seemed rather compelling. We couldn't think of any other way out. But as you're about to see, the calculations bear this out, and that is indeed what happens. So suppose Alice performs her experiment in a stationary laboratory outside a black hole at some fixed radius. She could use some rocket thrusters to keep her laboratory stationary. And let's just review what happens. So just some notation. There's a notion of affine time that I'll be making mention of with this capital V, which is kind of just time running along the horizon. It's a null time. But it's related to the little t, the killing time, which for our purposes is equivalent to proper time in Alice's laboratory by this exponential relationship. So Alice's proper time is this little t. And to begin, let's just consider what would happen if I took a classical electromagnetic charge outside a black hole, displaced it gradually to some new radius, and then just let it sit there forever. Again, this is some laboratory that's making this possible with rockets, etc. Okay, well, Maxwell's equations pulled back to the event horizon of a black hole take a really nice form. This equation just says that the affine time derivative of the radial part of the electric field is equal to the angular derivatives of the components of the electric field that are tangent to the two-sphere cross-sections of the horizon. So what this is saying is that a time-evolving Coulomb field gives rise to radiation falling into the black hole. And then this has a straightforward implication, which is that if you have a net change along the horizon in the radial electric field, in the Coulomb field, then, well, that means by this equation, you're going to have a net integral of the angular components of the electric field. But then just by the definition of the electric field, that means that you have a net change in the angular components of the four potential between early and late times on the horizon. Okay, so a net change in the four potential looks like this. Pick your favorite component of the angular component of the four potential and plot it. And this just describes exactly what I told you Alice is doing, but as viewed from the point of view of the field on the horizon. Initially, Alice's particle is at some initial radius, then it goes out to some new radius, and the four potential follows with this step function-like behavior. And this, to those of you who have studied the memory effect, will look familiar because this is an exact mathematical analogy of the memory effect at null infinity, but on a black hole horizon. And because this is at finite distance, this happens in any number of dimensions and not just in 4 dimensions. So we're going to be interested in calculating the decoherence due to becoming entangled with some field that does this. So we'll want to know the number of photons contained in this kind of a field configuration. And the number of photons, I noticed there's a typo here, but the number of, there should be a bar over this first A, or the second, whichever you like. Well, first of all, the number of photons is going to depend on the Fourier transform of A with respect to affine frequency. And that Fourier transform for a step function, or something that at low frequencies looks like a step function, goes like 1 over omega. So what that's saying is that the spectrum of photons is peaked near arbitrarily low energies. But if you plug in that field configuration's Fourier transform into the formula for the number of photons, you find that the actual number of such soft photons diverges. So for a permanently displaced particle, you have an infrared divergent number of soft photons on the horizon. Now, of course, Alice is not actually leaving her particle in the new position forever. She's going to bring it back eventually to do her interference experiment. But nevertheless, rather than that's this, and let's say she keeps it open for some affine time interval delta V, you're not going to get an infrared divergence, but you are going to get a logarithmically growing number of soft photons as a function of delta V. Logarithmic number of photons, it doesn't sound particularly bad if I'm worrying about becoming decohered by those photons. But then it's that exponential relationship that really kills her, destroys her PhD, I guess. Because now the number of photons is growing linearly in the proper time in Alice's lab. And this is the way it scales, where m is the black hole mass, q is the charge, d is that distance over which she displaced it, and big D is the distance, the Schwarzschild radial distance from the black hole. And this appears in the exponent of the off-diagonal element of her density matrix. So it's very, for a long t, it's easy to make this number bigger than 1, which then means her superposition is significantly decohered. And this is even if she's doing everything as carefully as possible. So adiabatic motion of her particle. Okay, let's just plug in some numbers and see how this goes. The coherence time for an electron superposed by a meter if you were to replace our sun, if an electron on Earth superposed by a meter, if you were to replace our sun by a black hole, would be about 10 to the 32 times the age of the universe. But if the experiment were done at the, say, innermost stable orbit, well, this d to the 6th power means it really does depend a lot on how far away you are, and then the coherence time is more like 5 minutes. Of course, outside of a realistic black hole, there's probably a lot more decoherent sources that are going to totally dominate, but this is just to show you can get humanly relevant numbers if all else is perfect. And maybe more interestingly, the analysis proceeds exactly as before in linearized quantum gravity, and all objects source gravity. So there is a universal decoherence effect on any object outside a black hole that scales like this. Now the only difference is this is d to the 4 now because it's a quadrupole type radiation. And although this 10 microseconds might give you some, optimism or pessimism, depending on if you care about detecting this or are worried about background decoherence, but you shouldn't worry either way, because this 10 microseconds is if you took the entire Earth and superposed it by its own radius, then a solar mass black hole where our sun is would decohere it in 10 microseconds. So I think in our paper we say that it would not be easy to make such a superposition. So it's a very weak effect, but it's universal, so that's perhaps interesting. You could also ask, what is the kind of local description of what's happening? Because so far I've made reference to horizons and hypothetical bobs hiding behind horizons, and this all seems very non-local, but quantum field theory and at least linearized quantum gravity should have some sort of local description, and indeed, as we showed recently, and also, well, a paper with Yanbei Chen, who's here virtually, and Wilson, Garo, and Dugard also recently analyzed this kind of a local situation. And, well, what we show in our paper is that outside a black hole, at low frequencies, the vacuum's populated by an arbitrary, it's pre-populated by a spectrum of soft photons or gravitons that goes all the way down to zero frequency. Now, that fact has been previously well known in the literature, but what we show is that this decoherence effect is due to a stimulated emission process stimulated by the presence of those very soft gravitons and photons that are pre-populating the vacuum. And you can, I just throw these formulas up here because I think it's kind of fun to think about. You can think about the vacuum outside a black hole as viewed from Alice's local laboratory point of view as having a fluctuating quadrupole or dipole moment in the electromagnetic case, or quadrupole moment in the quantum gravitational case, which has a power spectrum that goes like this. And the fact that, well, it goes like this at low frequencies. And the fact that this is independent of frequency at low frequencies is telling you that even as you go down to zero frequency, you still have photons or gravitons at arbitrarily low frequency. And it's okay, there's some nice generalizations of this story. Recently, Hongji Wei and Sam Gralla showed that the effect also arises with angular momentum dependent corrections in the presence of a rotating black hole. They also discussed the case of an extremal black hole, and there's some cool connections to the black hole Meissner effect. And then we also considered, well, based on the original thought experiment, a very similar story could go through in the case of a cosmological horizon. And indeed, the same thing happens in a cosmological horizon, just like the one in our universe. In particular, in a de Sitter spacetime with a horizon radius given by RH, there's an electromagnetic coherence time that you see here. And then there's this quantum gravitational decoherence. And this is all similar style of effect, but scaling differently due to the cosmological horizon that surrounds us. And again, it's extremely weak. If you tried to observe this effect, you'd need either superpositions on the scale of the observable universe, or you'd need incredibly large superpositions. But it's of interest for one other reason, which is that in this case, Alice's laboratory and her particles are moving on inertial trajectories. So if you thought maybe that this effect is due to the fact that the trajectories are accelerating, accelerating charges radiate, or you've heard something like that, that's not the end of the story. In this case, it's inertial charges that are subject to the decoherence. Okay, so just to summarize so far, black hole or cosmological horizon will eventually decohere any quantum superposition. Stress the word eventually. But what about the bobs in the interior that were motivating this whole conversation from the beginning? Okay, so this is where things get a little technical, and there are gonna be some formulas that will be probably inscrutable to anyone who's not in the weeds of this stuff. So I'll throw them up, but then I'll summarize what they mean, and I'm happy to talk about why they mean what they mean afterwards. But you can think of the black hole as a quantum channel, N, acting on some now arbitrary experiment carried out by Alice. And the decoherence of Alice's system due to the channel can be just characterized by this quantity, which I call d of n. For those who are following along, this f is the channel fidelity. Basically, this is a measure of, given an optimal recovery channel, how well can Alice recover any coherence of her state after the black hole has robbed whatever quantum information it can rob from Alice. In plain English, this is the decoherence of Alice's degree of freedom, or degrees of freedom due to the black hole. And in the previous examples, you calculate this, and it just reduces to the formula that you saw in Gautam's talk of kind of 1 minus the off-diagonal element, magnitude off-diagonal elements of the density matrix. But this holds in more generality. Okay, so then how well can Bob really do? The idea of kind of the information available to Bob or the decoherence due to Bob can be generalized. So suppose you fill the black hole with any number of degrees of freedom, arranged to perform an optimal experiment to distinguish Alice's field states. So I've populated my black hole with lots of different degrees of freedom. And you can characterize the information available to those degrees of freedom through what's called the complementary channel to Alice's channel. So the complementary channel is, just read what I wrote here, that's the distinguishability of the resulting interior states is determined by the information content of this complementary channel, which is basically the channel that models the effect of what happened to Alice on the system that purifies Alice. In this case, it's the black hole. So in plain English, this script I for information of the complementary channel, you should just think of it as you can use it to compute the probability of correctly determining the correct internal state given an optimal measurement, where, it's the probability of these guys correctly determining the internal state given an optimal measurement on the interior. And because we don't actually know, of course, from an exterior perspective, you don't know whether or not there are Bobs in the black hole or not, you could just as well take the point of view that this is describing the distinguishability of on degrees of freedom that describe the black hole itself. Now, I don't know what exactly that means because I don't know what microscopic or what degrees of freedom of a black hole are, but from an exterior perspective, you could just ascribe these degrees of freedom to the black hole. And just what we proved is just that the decoherence of Alice is equal to the information available to the degrees of freedom on the interior. So that's our theorem. It's just the decoherence of Alice's experiment is equal to the information about Alice's experiment that's available to Bob and his assistants in the interior, given they perform optimal measurements. Yeah, I mean, you could, I won't even bother reading the second one. Okay, all this talk about degrees of freedom makes you think, maybe there's some, what are some analogs? I mean, I don't know what black hole degrees of freedom are, but I can think of more ordinary systems that have degrees of freedom. Can I think of some analogs of this effect? Well, the first thing you might try to think of, does this have anything to do with black holes? What if I just took the space-time of a star, populated a quantum field in a thermal state outside of it? What we show is that does not give rise to this effect. Another thing that does not give rise to this effect, we showed, and also Yambe and friends also showed, that a global thermal state of Minkowski does not give rise to this effect. But Biggs and Maldacena did a really interesting analysis where they said, what if we, in flat space-time, we just try to develop a matter model tuned in such a way that it could reproduce this effect? And in the case of the electromagnetic case, they showed it's actually pretty easy to do. I mean, kind of a lump of hot aluminum could give rise to a similar effect. But I think quite interestingly, they found that in the quantum gravitational case, to mimic this black hole decoherence effect by some ordinary body of the same physical size appears to require some extraordinary properties of matter. So I think that's a pretty interesting line of inquiry to follow up on, an interesting thread to pull on, but that's where that stands right now. Okay, so, well, is this how much time I have left? Or, oh, well, we have a lot of time for questions then. So the summary of what I've said so far is that in the vicinity of a killing horizon, any quantum superposition generates long-range fields that register on the horizon. And this necessitates the emission of soft entangling gravitons, which the horizon in effect harvests, and those encode quantum information about the superposition in the exterior. So because all objects source gravity, all objects decohere outside of these horizons. And if, as viewed from the point of view of an external observer, the amount of decoherence that you experience is equivalent to the amount of decoherence that would be incurred on you if you were to populate the black hole with kind of optimal measuring degrees of freedom. And that's a precise mathematical statement, that the amount of decoherence that you experience is equal to the Witch path, or more generally, the distinguishability information available to degrees of freedom on the black hole interior. So that's all I have prepared, but I'm happy to take questions. I mean, I have some auxiliary slides, but I think the questions will be more interesting.
Well, since I was the chair, I get to ask his first question, right? Dan, thanks for the talk. You were mentioning soft photons on the black hole horizon, so let me ask you this. Usually, the memory effect involves BMS supertranslations, right? Which in turn is connected with asymptotic symmetry. So do you think that there is an analogy of those stuff near the black hole horizon?
That's a really interesting question. I mean, I think the answer is I don't know. It's possible. But I mean, the fact is that there are symmetries on the horizon of a black hole that are analogous to the symmetries at null infinity, but the charges are much more complicated. I mean, I think Ven Chandrasekaran, Kartik Prabhu, and Anna Flanagan have worked out some of these charges. And so in a nonlinear context, characterizing whether or not there even exists a black hole memory effect is difficult. I mean, Bob and Adel Rahman wrote a paper on that where they basically showed they were unable to find such a thing and showed why it's hard. However, in the linearized quantum gravity case, those problems disappear, and it is a direct analogy. But I would only take that so far as linearized quantum gravity. There may be a nonlinear version, and that's a cool question that I think, if anything, to me, this gives me some optimism that there is a physically measurable effect that scales in much the same way as the memory effect at Scry, and so it gives me optimism that perhaps with enough effort, such a thing could be found. But
it would be cool to find the analog of soft theorems, right? So you can have all sorts of memory charges, just like you have in the null infinity, right?
Yeah, that would be very, very cool.
Sorry, guys. So, that's then. Oh, you were not the organizer, so you can let this.
Hi, thanks. Interesting talk. So, given what you said about other objects not having this effect, it seems to me this depends on an horizon. Is that right?
Well, there are different possible ways I could answer that question. I'd say whatever, from the local point of view, whatever is going on outside your lab had better set up this this population of extremely soft gravitons that, and it's difficult to come up with, as Biggs and Maldacena showed, a matter model that generates such a population of extremely soft gravitons. Horizons do that. So that's the minimum requirement to get this effect, I would say.
Okay, so let me ask what I was going to ask anyway. Would this effect happen for sonic black holes?
I haven't thought about it. My gut says probably, but I really don't know.
Well, I think it should. It would be interesting to find out. I mean, because that's the possibility of testing some of this
Yeah,
stuff.
that would be very, very interesting to test, yeah.
So I've listened to the previous talk where there was another Bob who was superimposing spacetimes with horizons.
Yes.
So putting together your talk, you get a superposition of decoherences with different times, which sort of makes no sense, right? I mean, just to underline that my problem with superimposing classical bodies with different temperatures.
Yeah, I agree, you'd really have to, well, I think just like we heard about in the last talk, you'd really have to hone in on exactly the, here I can get away with using decoherence as a proxy for, what I really mean is, for instance, doing that spin measurement I talked about. Like you'd really want to focus on operationalizing everything, and then you could maybe make some progress in actually seeing what that might mean. But
In a relational state, that does actually make sense.
Mhm.
Relational interpretation picture. So in a relative state picture, that would actually make sense. I mean,
So you mentioned the possibility of analyzing this effect on cosmological horizons.
yes.
But you have a kind of, you have again an experiment with an idealized Alice experiment. Could you comment, have you thought about it in the concept of actual cosmology with quantum perturbations? Because there is a general problem of understanding how quantum perturbations generate the classical perturbations. So this, and you have super horizon perturbations that are there living outside of the cosmological horizon that could cause this decoherence, exactly as you are describing.
Yeah, no, I mean, we've been, Gautam and I have been, and Bob have been interested in that question for a while. I mean, we have a few ideas, vague ideas where we're thinking about along those lines, but there's a few steps that need to be overcome. I mean, the first thing is, here I used the fact that I have some laboratory to keep the particles, well, first of all, I had some superposed particles. If you were thinking of some inflationary type scenario, I would probably want to talk about really modeling the matter as a field and not just kind of localized sources. On top of that, it's not easy to see why the particles or the kind of concentrations of the field would be following the killing field. They'd more likely be following geodesics because there's no laboratory around to help keep them on track. So then the calculation's a little more tricky. So I think it's a very interesting question how something like this would affect cosmological perturbations and things like that, but there's some extra layers of challenge.
So I think my question is a little bit related with your answer. So how important is considering is, well, the question is, when you superpose, when Alice superposes the particle, is this superposition assumed to be free? I mean, is it inertial?
No.
Then, but did you consider the effect of this external agent decohering the system?
Good. Yes. Yes. So you have to treat the lab as being sufficiently massive that its own kind of center of mass degree of freedom doesn't decohere your superposition. But this is exactly the same thing that's already done every day in tabletop experiments. You know, if you have to, your lab always goes into a superposition. I mean, it's impossible to create a mass dipole, right? So your lab always goes, to conserve center of mass, your lab always goes into some small entangled superposition with any other superposition that you might be trying to create in the lab. And not all of that will be exactly reversed when you attempt to recombine your superposition, but your lab center of mass is sufficiently massive that its wave function is essentially overlapping the same amount as, it's essentially, you don't actually put it into a orthogonal states, unlike the quantum particle. So when you trace it out, it doesn't change the off-diagonal elements by anything on the same order of magnitude as this. Yes.
Yeah. So this assumes that the lab can be described quantum mechanically.
Yes.
Okay.
I was just going to ask about the difference. I'm not quite clear why the effect doesn't happen for a star but does happen for a material. What's the difference?
Good.
Those?
So that's I think the language I used could have been more clear. So sometimes if when a relativist talks about a star, as I think I did earlier, it means it's just the space-time of a star and the quantum field outside. That's what if you take the space-time of a star, you take exterior Schwarzschild, and then you have some matter shell, and then you have internal flat space-time, and then you put a sensible quantum field state on that space-time. But in this case, I consider it a thermal state. There you do not, and then you do the exact same Alice experiment in that space-time with a thermal state. You do not get the effect. Now, if you mean by a star something with lots of degrees of freedom that are becoming kind of optimally entangled with Alice, then you can cook up such an effect, and that's what Biggs and Maldacena showed in the electromagnetic case. Although it doesn't seem to be very feasible to do in the gravitational case. Just because, it's not clear what kind of exotic forms of matter have kind of G newtons appearing in the equation of state and where they would need to be.
If an experimenter were to try to do this in the neighborhood of a real star with lots of degrees of freedom, they might try shielding it for like E and M, you know how to shield it.
Right.
Would that cut out the effect? I mean, if you put this thing into if you shielded it from influences from the star, would you then lose decoherence? I mean,
it is possible to shield the electromagnetic version in principle. I mean, there's two things there, right? You'd need to make sure that let's assume that the degrees of freedom of the star has to have level spacings that are small enough to absorb these ultra low energy photons. And then your shielding so let's assume that's true. Then your shielding also would have to be extremely good at shielding ultra low wavelength radiation. If you had such a shield, then you could presumably avoid the effect in the electromagnetic case.
Is there a gravitational shield? It's probably not a question for you.
Not that I'm not aware of anyone ever having come up with such a thing, which I think that's why I use the word universal.
Well, first of all, thank you for this very wonderful lecture, Daine. My question is quite related to the first question by Professor John Donahue. I would like to know what is the dependence of these effects on the particular quantum state of the field. More specifically, in a Schwarzschild spacetime, for example, you can have the Hartle-Hawking Unruh or Bohr vacuums. And the Bohr vacuum in principle is very similar to a star. So would that also cancel any decoherence effects due to a choice of vacuum in a spacetime that still has a horizon?
Good. So the Unruh and Hartle-Hawking states are basically the same at low frequencies. So those do not change. And then in the case of the Bohr vacuum, let's see, did we find that it, yeah, Gautam remembers this. Yeah, there's no effect. There's a logarithmic effect, in the Bohr vacuum. Whereas there's no such effect. Yeah, that's right. So we actually, in our most recent paper, we have a remark about this. We just point out that it's often stated in the literature that the Bowler vacuum is a good proxy for the vacuum outside of a star. That's not entirely true at low frequencies, actually, because, well, as you can see here, there actually is a weaker but still existing population of low energy modes in the Bowler vacuums, giving rise to a logarithmic decoherence effect, logarithmic in lab time. Whereas, as I just said, outside in the space-time outside of the, a shell with exterior Schwarzschild and a thermal state, you get no such effect at all. Yeah, so they're not the same at low energies.
Further questions, guys? You again.
It's a very basic, maybe it's about the Galton presentation also. In the beginning you said you are working with the Newtonian field of Alice causing the decoherence, but Alice, the particle to perform the experiment, the Alice particle will have to move and there is some dynamics involved. Wouldn't including time dependence on all the things and so the space-time being dynamical change the whole argument or not? Or this is completely irrelevant?
Well, it's relevant, but everything we're doing is in the regime of validity of linearized quantum gravity. So there we're treating we can treat the background space-time as fixed, and then the perturbations are giving rise to are taking care of all the dynamical effects. Does that answer your question? Or there are some subtleties around the Newtonian field, but I'm not sure if that's what you're angling at.
So guys, let's thank the speaker again.